All right. Thank you, everyone, for coming to the session. So, as the title says, I'm just going to go through ArkLib, go into the actual code, and then also explain on the whiteboard sort of what the code means. So, in terms of what I plan to say, I will start with sort of the purely mathematical stuff. And then I'll go into the formalizations of IORs with some concrete examples, and also the stuff that I'm working on to make the IOR spec more readable and more scalable in terms of proving. Okay, so coding theory. This is, so if you went to the mutual CA session just now, we're formalizing all these definitions in Lean. And so I wanted to show, let's see. Okay, so here is, so first of all, this is what Lean looks like. Let me zoom in a bit. Is this good?
A bit more.
Yeah, a bit more. All right.
A bit more for the old people.
Okay. Yeah. All right. Okay. So.
Yeah.
Awesome. Cool. So this is what Lean looks like. You have an info view. I put it on the right usually, and that shows you sort of the state of what's happening in Lean. So if I click on, say, at some point like here, for instance, when you can see sort of clearly what is sort of on the game board. So these are all the like hypotheses. So you have, say, n, which is some type, and then you have instances on the type saying that, say, the type is finite and the type has decidable equality. And then f here is another type that is a field, it is finite and it has decidable equality. And c
is there something infinite somewhere, or
yeah.
There's an infinite. Okay.
So types in general are just sort of very underdefined. You need to put in hypothesis, even something as trivial as showing that, like, being able to compare two elements of the type and give you a Boolean result, that needs to be an explicit instance. Because otherwise, it's just going to be a proposition which sort of like carries no data. So that's sort of one of the many technical things that you need to work with when you work with Lean. And so this is the setup of a code. So this is C here, we define it as a linear code. So you may recall a linear code is a vector subspace over like f to the n for some field f. And this is Lean's notation for this. So in Lean, we try to make things as general as possible. And so we don't have a specific definition for submodule for subspace. We just have submodule instead.
So there is actually one, but it was deprecated.
Yeah. So people building MATLAB, they have like deal with the scalability issues a lot, and so they decided this is the best way.
So it knows that it's a subspace by the fact that f is a field.
Yes. Yeah. So you can always hover over these, and so okay.
So it's deriving that it's a semi-regular fact it's a field.
Yeah. Right. So yeah, this is a submodule definition. It requires that R must be a semiring and N must be a module over R. Okay. So that's just a setup.
And what's the n? N is mapped to f in the argument.
Yeah. So here you should think of this as vectors indexed by n. So n here could be the set of.
Okay.
Yeah, the arrows here, not really. You shouldn't think of them as like maps or anything.
So these are.
So n is the word length.
Yeah.
Well, the size
is,
of n is
yeah. N is the type
exactly.
of the
so
index.
N is actually meant as a set.
Yes.
So n
It's a type. Yes.
Yeah.
Mm-hmm.
So yeah, we have this is a functional programming language, so we use functions to express a lot of things, and so this just means you have you should think of this as f raised to the power of n, right? Okay. So let's go back here. We can define proximity. First of all, we just define like the number of elements in the finite field, such that the distance here is some custom notation. This is just the relative, no, the absolute distance between this vector and the code C is at most D. And we take the cardinality of this set. So this is just a...
Yes, it should look familiar. If it doesn't look familiar.
Yeah, I'll pause here for questions.
In this case, we're fixing the equality like combination, the R and 1 minus R.
For now, we fixed, but in the future, we'll generalize to like proximity generators. Yeah.
So this is delta theta, or is the theta like?
So this is absolute.
Distance,
Yeah, we can go to definition here, and it's just the distance from the code that right. So we define this to be sort of the minimum Hamming distance between U to any vector V that is in C.
I see.
Okay.
Yeah.
I see. I was wondering why there's like not just delta, like a little theta near it.
It's just
Just a name.
yeah, just a name. Yeah. So we can
That's
define
Sure.
lots of custom notations.
Yeah.
Yeah.
But it's not a parameter, it's just the name of the operator.
Yes.
So
I think it's because I think there already was a delta in the previous information seriesing in MathLib.
yeah.
I think that's why.
So that's why there's a prime. Because yeah, you can see sort of stuff that is in blue is the notation. Okay.
The
So
prime is also part of the notation.
Yes.
yeah.
So the proximity measures counts the number of good randomnesses.
Bad, I guess.
What is
Or-
feedback dot found?
Bad randomness. That is
The randomness is
or-
going to give you like something close to the code, which
Yeah.
might be good or bad depending on what.
yeah, depending on
I call it always the good.
Okay.
It's positive.
okay.
You know, you want to deduce correlated agreements. So these are the randomnesses that brings you close to the code.
Yeah. Yeah, and then you have the proximity gap definition, which says that whenever you have two vectors U and V, such that their measure is more than a certain bound, then the distance between the interleaved code, the interleaved vector U and V, and the interleaved code. So here it just means it interleaved itself
With two.
with 2. Yeah. So the exponent is 2. Yeah. Is at most D.
Okay.
Okay.
Just for personal curiosity, what do you call the beautiful and ungodly symbol with the two triangles?
You can mouse over.
Yeah. It's a bow tie. You can always hover and then you see how to type it.
Yeah, but
Yeah.
Yep. No, just double check.
Your eyes are still working.
Yeah.
Yeah.
I'm learning a lot of LaTeX and
Please don't teach them.
Wait. But in the comment above, you use the
Yeah.
tensor kind of thing.
Yeah. I guess I
So
should.
that is the opposite,
Yeah, because I think like tensor is not exactly the right thing, right? Because tensor code is different from interleaved code.
Yeah.
Okay.
The word tensor is super overloaded in this.
Tensor is overloaded in every field.
Could you go again?
Don't ask your physicists what they mean by tensor.
I mean, yeah, technically interleaved is tensor with the identity code.
Yeah. Okay.
So that's one PR for this session.
Yeah. And then you have correlated agreement.
Can you scroll up for a second?
Yes.
For my understanding, so then on proximity gaps is if the number of good randomness exceeds certain the bound,
Mm-hmm.
then And next line, is this a conclusion?
Yeah,
Yes,
next
Okay,
line.
that's
Yeah.
a conclusion. Okay, yeah.
Yeah, then it must be close to the interleave. Okay. Yeah. So, yes, let me keep going, and then eventually we'll get to the main lemmas of the proximity gap paper, which is unproven, of course. Okay, so the next thing is just plain correlated agreement. So this just says there exists a set of large enough size, such that there is also a tuple of code words from 1 to k. So that's why we have the spin k index here at the beginning, where for each I, this vi is in the code, and that it agrees with the vectors wi at exactly the set S.
Come again. Okay, so C is the code, delta is the distance, K the
K is some parameter.
the number of code words.
Yeah, the number of code words.
Okay.
Yeah.
W is the
It's just the vectors of it's just a vector that does not need to be code words. Can be like far from the code words. Sorry?
the input words.
Yeah, it's the input words.
Yeah.
Also, it's from K to N to M, so that's
Yeah.
like from K by N to M. So this is,
No, it's K of them of like them.
So
Yeah, so-
you should think of this as K vectors.
yeah, is this currying that they haven't?
Yes. Yeah. So currying is
So
always
it's like K times N maps to N.
Yeah.
In some sense.
Yeah.
Okay, and you're saying if there exists a finite set which is large enough,
Mhm.
and there exists V
Collection of
It's
code
again a
words.
selection of
Okay.
words.
So this K to N to F means just you have K code words.
Yeah.
Wait, where are we taking the
It maps
combination?
from K to a function that maps.
So we don't have the combination. We just have the code words.
So it
In
is
terms
a
of the-
correlated agreement between the different words.
Yeah, between different words.
I see. Isn't that just distance in the interleave code?
Distance.
Like if I have like a bunch of code words that they have correlated agreement, that means that they also have like a small distance in the interleave code.
Yeah, I think.
Yeah, okay, so this is
We-
the distance of the interleave code. Okay.
So this is not the batch thing, there's no,
No, there's many of them.
no, but I mean, this particular one, it doesn't, it's not.
Yeah, this is just the definition of distance.
Okay, the generic one.
Yeah. Okay, that makes sense. I thought this was already the theorem with the batching, but it's just a definition of distance for the interleave.
Yeah.
I think it's just my gut feeling, formalizing correlated agreement by means of the interleaved code or the interleaved words has some benefit, even in other applications. You know, when you in the end want to argue the whole security of the Stark protocol on top of RAI, it's so often exactly using it simplifies proof writing, at least paper pen proof writing a lot. Just saying, okay, this is a correlated proximate at that distance, and because you need to argue in the end about the number of such possible interleaved proximates or correlated proximates. So just as an input, maybe it makes sense to abstract it also that way here. I don't know.
I wonder, like, to me, the notion that took before is that the distance of the interleave code, you could, maybe this is a pain, but you could also think of linear codes where, like, the alphabet is not a finite field, but it's like a finite, like, something that supports addition and multiplication, so like a ring, like, a vector, and then you can, like, give already the interleave code, then becomes a linear code, because otherwise it isn't. And then this becomes just the distance of the interleave code, and then maybe you save a definition.
Yeah.
Yeah.
Great. Cool. So the scrolling down to the first lemma that we state here. So this is the theorem 1.2 in the paper, and so
Is
it's
it the Delicamp-Welch theorem, or which one is it?
It's
the
just that the RS codes have proximity.
Yeah, it's up to Johnson. They have
Yeah,
already.
yeah.
Up to Johnson, right?
Yeah.
up to, yeah, just
But
Johnson.
So
So-
when you say Ethereum 1.2, in general, when you reference Ethereum.
This is the proximity element assessment.
Sure.
But
Which
the-
ePrint
the-
version do you cite that?
The latest one, right? We can generate a bibliography to show that in the blueprints PDF file.
I want
Sure,
to
but
write-
if they update the paper and the theorems get renamed,
Yeah, sure.
No, I'm writing the documentation now with the actual statement, so even if they change it, you can just read the statement.
okay, but I mean,
Even compare.
yeah, you could just point to a specific ePrint version. That would be probably
You can.
yeah.
But most of the time, like what you want is we'll just, instead of saying theorem 1.2 of this paper, we'll just write the like plain language
Sure,
statement.
But this isn't published.
But this guy doesn't.
Yeah, but they updated the ePrint after publishing it.
Yeah, but if you point the.
Oh, you point to publish, yeah, sure.
Okay, and
No, but if you point to the published one, that's even worse, right? Because there you have most stuff is in the appendix, or it's like
Yeah,
not
yeah,
even in
so
the.
the publish
so-
is quite substantive.
Yeah, always point to the ePrint, and in these cases, I would even point to a specific ePrint.
Yeah, that's just changing the bibliography.
Yeah.
It's not a big, like these will just comments, right? They're very
So is this correlated or no correlation?
So this is just the proximity gap. And so it states that for all delta, that is at most Johnson bound, then you have, right. And C here is just any sort of T set of vectors. Yeah. Okay, so you have this.
They're code words, no?
They are not necessarily code words. At least
I thought
the
it's
Reed-Solomon code. Yeah. So the Reed-Solomon code is sort of uniquely defined,
Yeah.
given the domain and the degree.
Okay.
Yeah.
Mm.
So the code is fixed. It's the C that gets turned into, I guess, an affine space. Maybe Katie, you could narrate this
Yeah,
definition.
so this definition, you have an affine space, and then you generate a collection of T affine spaces. And this is what this line will tell you. It gives you T affine spaces inside F iota in that case, so the vector space dimension iota. Which is how the theorem is stated.
so this is kind of like I have all these code words and I look at the affine space pattern by them.
Yeah.
Yeah. Okay.
Oh, well, not the code word, these words.
Is it ever used somewhere the affine space variant over the line?
Affine space over the lines.
Well, yes, there
Yeah, you
are
can-
certain proof systems that use separate randomnesses for each of. Okay, got it.
Or
And
instead of using pallets.
No, even just like the two, because the affine space proof, as I recall, which addresses like one randomness for each of the component words, that's just a like easy generalization of the single two words only.
Yes.
One random.
So this is the most general version of
Yeah.
which kind of has all the theorems in it. Then we have a statement for each thing. So a statement for the affine lines and then parametrized curves and so on. And then the randomness would be different.
I see. And in this there is no eta because the eta is already accounted in the error bound because the error bound will get
The error bound
from,
gives you the pair.
for the-
Yeah, you can go to the error bound definition in the same file, basically. And it's, so first I'll read, you should read the comment and then I'll scroll down to the code. Okay, so it's just, you have the two radius, and here, first you define the rate, and then you do an if statement. So this set.ioc is just a sort of left open, right closed interval. So if you hover over the comments, then you'll see this is the right definition. Then, so this is the unique decoding radius. Then you have the simpler segment, and then if it is between unique decoding and list decoding, then you have this m parameter, and the error is in terms of m. This is the
The ceiling appears to be vibrating. Quite a bit. I'm not sure you guys want to stay there.
It's fine, at least enough.
It's your lucky piece.
Sorry.
Yeah, no, it's okay. Otherwise, it is 0. This is the It should always we should never reach that in Ethereum.
Yeah.
Okay.
Very quick question out of curiosity. Obviously, this is a development question, which was you weren't a big fan of the notations we introduced for ranges. Was there a reason for this? Out of curiosity.
I think it's kind of hard to maintain. Like, future notation may clash with it.
Yeah. So because it uses brackets, we tried to add the subscript to create more uniqueness and the parsing of this, but but still, you thought there was still too much of a risk. Okay, fair enough.
Yeah.
Okay.
I will have another question out of curiosity. How long does it take to write this statement? In terms of like, how long did it take? Like
To write this statement.
I think this is fine.
This one's quite fast.
I mean, I think Katie, you wrote this, right?
Yeah, this one's quite fast.
No, I mean, like the this
whole-
together with let's say
The whole file.
the correlation agreement. How long did it take?
Well, it depends because, for example, for this one, I had to use some affine space library from ArkLib, which was kind of difficult to understand, so it took more time because of that. But if you don't use new libraries, it could be fast. It's just for me because if I get to understand the whole new.
Yeah, but the ballpark. I don't want to like the seconds.
I didn't time it. I don't know.
Would you say it's a few days? More than a week?
Oh no. This particular theorem, I don't know.
Okay.
No, I mean, I think they also the whole proximity gap file, right? So I mean, I think overall that took, I mean, including review.
With reviews, yeah.
Yeah, with review that took a few weeks, but I think the actual writing, the main writing of all of these results was in the order of a week or so.
Yeah, the order of the week, 2 days of which were spent on affine spaces market library.
Yeah. And this, of course, like this will be better because the more, let's say, library you have, the less time it will take in the
Yeah,
exactly.
the more you familiarize yourself with market, for example, you get faster because if you have to use it again, now it's
You understand how things are defined.
Yeah.
And I mean, I think as well with these, there was quite a lot of backlog that was needed. So defining linear codes and read-Solomon codes and things like this took a bit of time just because it didn't exist before.
And actually, I think one point that's actually quite important, which was before Katie joined Nethermind, she had no lean experience whatsoever.
Yes.
So this is actually, I mean, it took a week for someone who's a total lean millionaire. Well, I mean, now you're no longer a total lean millionaire, and I'm saying that with all respect. By the time that you wrote this, I think it's fair to say that you were just starting.
I think at this point I had like a month of lean experience at most, and I haven't done any programming before because I just did mathematics my whole life.
Right.
So yeah, I suppose it's easy to pick up.
Yeah, for sure.
But I don't,
I mean, as you can see, a lot of the notations are very similar to what you would have on Amazing, right?
Yeah, but they're like, you always compile your proof.
I always write sorry at the end.
Well, this is at the start of the proof.
Sorry.
If when you don't have a proof, you can write sorry, and then the lean type checker will throw a warning but not an error.
Okay.
So it allows you to still compile your file with warnings instead of having.
So my file is like this, sorry.
So, I mean, this is a blueprint, so we have a few a bunch of the proofs are closed, but a lot of the more complex ones are just sorry out the call.
I mean, for Johnson Bun, I would expect that it would be sorry for a while. The proof is
Actually, no, I do want to show. So this is basically the end of the files. It's just we state all the main theorems of the proximity gaps paper. Okay. So this is unproven. Let me go to some proven things, which includes the Johnson bound. Yeah, we have the statement. Yeah. So for instance, this is Johnson bound.
I don't think nobody ever proved Polish-Spielman normally.
Yes, well, we're about to find out.
Polish-Spielman. It did like a theorem or like agreement look of like a multivariable.
In a theorem prover.
Yeah.
Okay.
No, no, I was joking that nobody has done it in general, but because the proofs are very convoluted, bugs are found. It's
actually is quite easy and understandable. Look at the original paper first.
Yeah, I have.
Look at the unique bounds on the quotients.
Yeah.
Because they had a gap at the original.
Yeah. Eventually I will. Let's put it off for a bit.
It's once you understood this idea that the result have so long in questions of the discrete.
Yeah.
I would say for retirement.
Yeah.
I would say for retirement to understand. For when I'm retired.
Yeah, actually, this is quite a nice thing to show.
The what? Then it's here?
Yeah,
So tomorrow.
So, okay, yeah, cool. So here is the supposed proof of the Johnson bound. Yeah, so.
So you mean you prove the number of approximates?
Yeah, the cardinality of the set B is almost this much. Yeah. Well, I guess the problem is you see this proof, you see no sorry in this proof, but you don't know if there were any sorries in any of the lemmas that this proof uses. And so that's where we get this print axioms, where you can actually print out whether there was any step in the process that used the sorry.
Yeah.
And so
can we go through the proof that I get an impression?
Sure. Yep. Yeah. So
I'm gonna make the info view a bit bigger, maybe, so that way.
Yeah.
Is this the full proof of
I'm not yet retired.
The Johnson bound.
Really?
Johnson's
theorem.
Johnson's
proves
theorem.
that your polynomial approximates up to Johnson bound. Also misunderstanding when you were mentioning that it was not the proximity guess.
Okay.
The proof of Johnson.
Okay, got it. Okay.
Yeah.
Because this will be the length of the...
No.
Well, we could hide all the complexity in the lemmas.
Sure.
Yeah.
No, I think it's called Johnson's theorem.
Yeah.
Just theorem 5, yeah, sure.
Yeah. So yeah, I guess.
So let's start.
So we say that in order to prove this, it suffices to prove the following, which.
In order to prove what's the statement? Let Q. What is Q?
So maybe scroll up a bit and we can start from the statement.
Yeah. Q is the size of the field.
So we have Q over Q minus 1, and
Yeah. Join us.
So Q, condition is Johnson condition. What's the B?
B is some set that satisfy the strong Johnson condition, which is some condition.
Let's go to the definition.
Yeah. Just that.
So I find set.
Something is positive.
Wait a second.
Yeah.
Yeah. It's wait. This sounds to me like 1 minus something like 1 minus rate squared.
Mm-hmm. So E is this EBV or E is
no, E is the error, so that should be the agreement set size, square of the agreement set size is square of the agreement set. Could you go back to the definition?
Yeah.
So condition. What does it say? Could we just sorry?
No. This is great. Good. Yeah. This is good.
Okay, so we have a finite set B, and then we have what is I have a finite set N and a function on N. So any word V is also another function on N.
E and D are functions on B and V.
Wait a second. Why?
So this points to a definition in this in this other file, where you can see exactly what E and D are. So this would be.
We have functions named E and D in the Johnson namespace.
Yeah.
Okay. Maybe we could.
Yeah.
Descriptive names in the future. So,
Just understand what's the condition strong is. So what is it without lean? What is E is the number of errors, the distance more or less, or D is?
So E, I think is like the here like the average distance between V and the set B.
yeah.
So this is you take sum and then you divide by the size of B.
It's this kind of with the average distance.
Yeah. And then D is the sort of the
I wouldn't be able to parse now because I recall only what's often called the Corradi lemma. But maybe average distance is there also present.
Must be. A technical question, assuming it makes sense. How do you run any of this? Let's assume I want to run Johnson. Does it make sense running anything, or is it compilation?
So technically, yes. If every definition you use is computable, then technically, when you compile the program, you can run it.
So, but let's assume that I do something wrong, right? Not on the definition, like on the, I don't know, on the proof. How will I know?
So
I don't know compilation time, or.
So there are two. So one is, are you defining something that is wrong in a sense that you write down a statement that does not satisfy the type checker, and then you will get an error.
It's compilation.
Yes, you get an actual error message that says this isn't type check. We might say we can't infer this type instance, or you've done something which doesn't satisfy.
And this happens when I write, or I have to take
so actually, it happens. There's an LSP, and so you don't have to actually build every time you can get an error message. But technically, yes, it'd be when you compile.
Like this is already compiled.
Okay.
Yeah. But then obviously the other mistake you can do is that you write down something which passes the type checker, but which is not the statement that you actually want, right?
And then in this case, when will I know?
When someone tells you you're wrong. Like, because you can write a true valid statement, which is not the statement that you want, right? Same on paper, right? You could write a definition which does not actually define what you intend to define.
On definition, but on the proof, I mean.
For the proof, if you're happy with your theorem statements, then you cannot produce a proof that is valid and passes the lean type checker.
At completion time.
At completion time.
Okay, got it.
Yes.
So what is the proof that I write down is wrong? The type checker would say.
Yes.
The type checker.
You will get an error message that says
failed.
When do I ever need to run things? Never.
Yeah.
Does it tell me
for these kind of theorems?
Never.
Yes, it tells you exactly what it is. It will show the exact step in the proof where there's a mistake.
For instance, we do have a modular fry, right, that we can run.
Yeah.
Modular, we haven't integrated with computable modular stuff yet.
But we'll have a look at the model for it.
Yeah, but that one you can put values.
But if you want to see what maybe we can like break the proof quickly and then show what it is. We can break the Johnson bound proof. And then so we can see an error message of proof breaking.
Like that.
Okay.
Fix it later.
Sounds great.
Yeah. But anyway, okay, so if I have the fry module, I run it, and then I can prove that this fry module satisfies some things that is compile time, but I can also run it as a program.
Yes. Exactly. But basically, when you have the theorem that says this construction has round-by-round soundness, the construction is an actual executable program.
I see. Very nice.
That's the appeal.
So here you have a suffice statement, and you have to justify why this suffices for the conclusion, and this line here is the proof for why this suffices.
Yeah.
So if I were to delete something.
we can remove linears.
Yeah. So for instance, if I don't have this, then lean is gonna complain.
Oh. Yeah. So immediately actually have the feeling.
Yes. Yeah, it's instant. That's the appeal. And so you can see it'll say unsolved scores if you scroll down on the info view. You can see here is the unsolved goal, and then it'll give you some kind of error message.
Yeah, and it's this goal right here that is unsolved. You need to show that this Johnson denominator is non-zero.
Perfect. Nice. Great.
Yeah. So it's really good because you can basically not understand what you're doing, and you won't do something wrong. You can get guided. Yes. But you can get stuck in a loop, I guess. But but you can't believe that you have something that works.
So there are further learning progress. Like you might make progress, but definitely will not be worse.
Yes. And you can see as well, maybe if we add, can we add like a dummy rewrite for like using some lemma that wouldn't work, and then you can see it will find like, oh, it doesn't find like a way to apply this rewrite.
So for instance,
oh yeah, we apply sim.
Yeah, so all these commands are called tappings. They are for you to prove theorems. And so we have a bunch of these commands. I think the most the most used one is a simplification. And it just tries to simplify the goals based on a bunch of lemmas that it has. We have registered as simplification lemmas. This linear thing is a sort of linear arithmetic solver that takes in all the hypotheses, and then it will solve the goal for you if it's something like this. Something like something is not equal to something is less than something, and so on. So is that what you wanted to?
I was going to say if we try to do like a rewrite with a lemma that's not actually useful, and then we can just show the error message, just like, oh, you tried to do this, but we couldn't apply this rewrite.
Rewrite with Mala song or something.
Yeah.
Right.
Yeah. For instance, this is another lemma.
Oh yeah, but you don't want that field simp. I think that you just.
It doesn't matter. We'll get.
Okay.
Yeah. And also these tabs are like I use IDE with AI suggestions, so it just gives me stuff.
Suggestions which may or may not work.
Yeah, most of the time they don't work.
But yeah, so I think that you should have like if you scroll down a bit in the info view, there should be some message that says that like Molasok didn't do anything, I guess.
No, so this does do
Molasok,
something because there is
you've got some
something that can be reassociated.
Oh, you can do we have like, if we try add 0, I guess, to do nothing, right?
Add 0. Yeah.
There's no something plus 0.
Instance.
Yeah.
So
what is RE?
Rewrite.
Rewrite.
So it's just rewriting a term in the proof state.
So it says rewriting your goal with this quality.
Yeah. So if you try to rewrite using this lemma here, which is that 8 times 0 equals to 0, then you will get an error message. I think if you scroll, you'll say tactic rewrite failed because it didn't find an instance of this, and so it can't work. So you get like kind of decent feedback about why what you're trying doesn't work.
You had a question.
I answered my question. Excellent.
Yeah, and now we fix the proof again.
Cool. So that's all I wanted to show for the coding theory because I do want to move on. Yeah.
And then actually, because the exact step at the end is probably automated, right? Is that an apply question mark or an ASOP question mark?
Oh, is there?
I'm thinking about the exact step at the end. The final step in the proof.
This was a specifically crafted lemma.
Oh, okay.
This was specifically crafted.
Okay.
Okay, so now I have another question. And maybe this is a good one for Ulrich. So lean is constructive logic, meaning it will not support things.
It supports classical mathematics.
It's a what?
It supports classical mathematics.
Yeah.
You don't have to be constructive.
Oh, interesting.
So unlike Rock, it actually has a separate type universe for the propositions, which allows propositions specifically to be non-constructive, while allowing the rest of the types, the data types, to be constructive.
Okay, but so is the calculus of constructions constructive?
Yeah, calculus of constructions, as the name indicates.
Okay.
But we can add in this law of excluded middle so that it's used a lot in MATLib because mathematicians don't care about choice or about constructiveness. So we can always just add it.
In fact, actually, if you look at the printed axioms, you'll see it doesn't necessarily depend on the law of excluded middle. It actually depends on the axiom of choice. Because in lean, we construct the law of excluded middle from the axiom of choice using the Diaconescu's theorem.
Fascinating. Okay.
Is that the same Diaconescu as?
No. This is a guy called Radu Diaconescu.
Okay. I thought it would be a funny coincidence.
No, but a significant number of Romanian logicians are called Diaconescu. But this was a guy who did his PhD in Canada, and then he published a single paper in which he published Diaconescu's theorem, which was very impassioned. And then he quit his PhD, and there's apparently no trace of reply. He just published this one paper in which he proved sounds like he didn't
This is what you want to be like the way you want to.
Oh, really?
What is that?
Oh, okay. Interesting.
So
kind of model.
Let's refocus, maybe.
To prove something like data or whatever, and they didn't know why, because it was just a Romanian PhD student, not well known, and then actually his publication was impacts a lot.
Yeah, it was gigantically impactful.
But this was done later when I think people in Germany helped him to get data or needed or whatever.
Oh, okay. I hadn't heard this story. This is interesting. Okay.
Yeah, maybe find it again.
I'd be very interested to see this. Yeah.
Not even
Yeah. Yeah. Okay. Interesting. But yeah, so this guy apparently.
Okay.
Yeah. Sorry.
Okay. So now I want to maybe get people's opinions. So if we were to formalize the proximity price, the statement, right, in Lean, using, say, let me go back to the proximity gap paper, here, coding theory, right? If say this is the way that I showed how we define it in Lean, what is your thoughts? Like, would you accept this as a valid statement of the theorem? What would make you gain more confidence that this is actually the right theorem that we formalized?
Would it be like where you put the else 0 to change with the? Because I think like if you click on error, where you showed before, right there you can plug where there's
this error.
No, before you were going where there's like the unique decoding, this decoding, and then there was else return 0, something like this. Right?
Yes. So yeah,
this is the definition of error bound.
Exactly. So no.
So well, I mean, but okay, ignoring what the errors are for now, like okay, so you would have to change the dot square root rate to just rate in the part.
Right.
This is fine because we're going to capacity. Then you have like the rest. Okay, you're saying that. So okay, maybe as an okay, so this is a theorem. It's something that you can write as a story.
Yeah.
And seems good. Like for other things that's being formalized, how do people can get confidence? Okay, actually, I'll tell you what. There is a way you can get confidence that these are the right theorems, and these you use them to prove something. So you go there, you say like, look, I do a mock, say some check with the code folding, for example.
Right.
I use this to prove it, and if it allows me to prove this statement, then it is the right theorem. So this is, for example, like we had recently a paper on like UC security. And well, I had one and ran and another one, and when the question was like the functionality that we're trying to achieve, is it the right one, right? Which is a similar thing that what you have here, because you have something that you want to achieve and you want to figure out what's the right one. For them, we say like, look, there are some other well-known functionality that we care about. In particular, for example, there is in the UC case, there is signatures can be made from a proof system, and UC secure signatures are very well known. So we like, look, go and prove that you can, from your functionality of a proof system, you can build the functionality of a signature. So to me, the way that you prove that this theorem is the right one for the conjecture is that you take like either the old Fry protocol. I mean, Fry needs weighted, so it's a little bit different. You can do it with mutual as well. Yeah. So if you do this kind of thing, you have the protocol, you have the code, the protocol of the code, so you have confidence that this is like the real thing that you're running, and if you can prove security of that, then I'm confident this is the right definition, because from what I seem to understand, like look, then you could prove equivalence with another Fry protocol, but if you show me the code and the code folds things that it should fold them, and the verifier check what it should check, then I can prove that this is secure, then this is a good enough definition for me. So I think this looks good. If I want to get the full confidence, is that I use it to prove something real. Maybe this is the best way. What do you guys think?
Yeah. I think we should be able to do that.
Yeah.
Quick question, since you mentioned the price before showing this, is this the mutual correlated version?
No.
This is just correlated.
Yeah, it's just whatever that theorem states, which is not mutual.
I mean, theorem states
the same now, right?
Johnson bound in a sharp manner. So
no, but the eta is accounted in error bound. Error bound gets delta, and with delta it computes eta. So
the eta is enforced to be non-zero.
Well, in computing, the error will be infinity in this case, I assume.
Yeah, but then the theorem is probably that would not hold. I'm not sure how it treats in 1/0 in this case.
But you can prove that when delta
is 1, right?
yeah, the error is 1 or infinity.
Okay.
Yeah, so it's a trivial statement in this case, but I assume this is what you're doing, right?
Yeah, yeah. So yeah, I think the boundary conditions are especially important and especially easy to misformalize. Yeah.
We had a problem with this division by 0 recently too. Right?
Yeah, yeah.
And the British experiment that, yeah.
Mm-hmm.
It turns out that 1/0 is equal to 1, I mean. Is equal to 0, sorry. So obviously. So because the functions have to be total, so they have to return values for everything within the.
So 0 to the 0 is 1.
Also, yes, I think so, yeah. So, but that meant that we had a sort of like one of these boundary issues on the British experiment memo where actually there was a condition that was meant to be unsatisfiable that actually was satisfied.
It was always satisfiable because of that. That's one of their main.
I mean, there are like 3 hard things in computer science, which is boundary condition, off by 1. That's it.
We've had some off by 1 errors as well.
Sorry?
We've had some off by 1 errors as well.
It's very discomforting though, so like every time you divide, you need to just remember to check that the...
Well, no, because I mean, either your theorem happens to hold, when either you're going to prove your theorem and it happens to hold for the case where whatever your denominator is 0, right? In which case you get this right as this, or it won't for that specific value, in which case you need to add the extra condition that the denominator is not equal to 0. Right, but you're still going to get it wrong if you prove it. If I'm making sense here.
I don't know.
Okay. But I'd say basically either it doesn't make sense for this extra value that you wouldn't have, right? Either your theorem is still true and then you can disprove it as is, or it isn't, in which case you're going to have to add this condition.
But it doesn't mean what it normally means.
It means what it normally means everywhere else apart from this one value, right?
Yeah. Okay. So yeah.
Yeah, let's do items.
Okay.
Yes.
So what you said about like defining phi, proving soundness depending on correlated agreements.
Phi, or even like simpler thing like league error, you can prove with mutual or with CA. You can, just if you prove more protocol, of course, I'm more confident. But with a single one, I think is a good target to go for.
There's even simpler statements, right? You have theorems like folding preserves this.
Yeah.
You could prove that.
Absolutely.
And if NCA is correctly
defined, you'll be able to prove it. Otherwise, you won't. Yeah.
So without having to go through the whole thing.
Yeah. Yeah, but of course,
You'll have to do it eventually.
Yeah, eventually you will have to do it, and this is where you get the full. Yeah.
Okay. Yeah. So let me go to the second part.
Maybe a very stupid once I prove a bounding like lean, right? Yeah. So I know all of this. Is it possible, like for example, say that I'm running my fry and I want to then get the parameters, right, for it? Is it possible to then like use this to like spit out what the when I tell you K and N and stuff like that, I can automatically compute all of this because it's all runnable?
No, because well, if everything stays rational, then you can.
Yeah.
As long as you have like a square root or anything that's a real number, then you cannot, because real numbers have to be exact, right? When used in proof, it has to have the exact semantics, and so you can't just like run like square root of 2 when you run it on a computer. It sort of truncates somewhere. Right?
So not in that blue. So the ITF standard for floating points is extremely messy because they're not uniformly distributed.
Yeah. Yeah.
So you wish.
So there are ways you can like take a real number and then convert that into a floating point number, like actually do the computations, gives you some floating point numbers. That requires work in the end.
Okay.
To settle that.
Requires work in general. So this is why actually if you try to, a lot of differential privacy implementations back in the day were broken because they thought they were sampling real numbers, but they were sampling floating points, which are not the same.
Yeah, turns out. Yeah. Okay. Because there would be something, if you had the proof and all that, and then a way to like say like, look, this protocol with these parameters give you this bit of security, and I can like really extract them. Eventually, long term this might be nice.
But you can prove prove that if this is the real expression, then this is like less than 2 to the minus 100.
Yeah.
Yeah.
Good.
Okay.
I mean, alternatively, we could also write a function that gives you a lower bound to your bits of security with a proven error. But as you said, it requires
It requires work, because you have to bound the floating point computations. Like it always has to be a lower bound.
Yeah. It's not trivial. I'm not
Yeah.
claiming it's trivial.
Yes.
I'm saying it's possible.
It is possible. Okay. All right. So let me go to just now coming to the interactive Oracle reduction parts. So something that is like 1 or 2 page in the preliminary sections of the SNARK paper, like when you define what is an IOR. Right? You think of it as you have some interactive protocol. Here you have some prover, and here you have some verifier. They interact over a number of rounds. And the prover, let's say, it knows the implicit, have this thing where X is the explicit instance, Y is the implicit instance. So maybe let me bounce this Y for the verifier. This just means the verifier only has Oracle access to it, and W is the witness, right? Okay, so this is the model of IORs that you would see in papers, but turning this into a like a definitions in lean, and then writing that definitions in a way so that you can actually prove things about it is pretty non-trivial. So let me show what we have in here right now, and which is still not the optimal definitions. But you can think of, say, when you start formalizing, you have to make a lot of choices. So here's one choice. How do you define interactions? Do you define it so that it sort of alternates between prover and verifier? What about alternating between verifier and then prover? And what if you just don't have anything at all? Right?
I mean, there are some definitions that also don't explicitly have a verifier algorithm, and they just say random challenges.
You can define everything here is like random.
And verifier algorithm is just the very last thing.
There's something here. I agree. So the convention that I went with is that I do not enforce any sort of interleaving of messages. This is so that I could sort of break the protocol down into sort of more modular layers. Like even a single message from the prover or from the verifier could make for a meaningful IOR. And also when you compose things, oftentimes the structure doesn't sort of continue, and so you have to do like some padding rounds. Let's say if you have like a Sigma protocol, right? It's just free message. If you enforce that the verifier must respond, then you just add a dummy message here, and that's just like unnecessary complexity. Okay. What it does mean is that now if I just give you, so here you have like a vector of the direction of the message and the type of these messages. Okay. You don't necessarily know that, say, all the challenges must be in even index, and all the messages are from the prover are in the odd index. Like we don't know that. There's just like some definitions that we define on this where we just filter out based on the directions.
And I could send like 3 prover messages in a row and then a verifier message in a row.
Exactly. Yeah, exactly. And so.
Sorry. So because you say the direction of each message in the protocol. So the process just now a single small reduction, like.
So protocol still has could have many messages.
But so there's only one direction you can sense?
No. So direction here is
of each of the messages.
Each of the messages.
Yes.
So let's say you have 10 rounds.
Yes, okay.
Yeah.
Got it.
So index size. Yeah. Okay. Thanks. Cool. The next thing we want to tackle is how do you define Oracle access? Especially when you say the prover sends a message to the verifier as an Oracle. So,
Question just, we are not considering the holographic setting at all at the moment.
what do you mean holographic?
When you have like an indexer.
No indexer.
Okay.
Yeah.
So does it even matter for lead that we have Oracle access here? Because we are not trying to prove anything about the efficiency. Right? Would it be sort of
Oracle.
just ignore that it's an Oracle and just assume that this whole thing is sent to the verifier?
You cannot, because then you cannot do the BCS transformations. Like you need the explicit information that something is an Oracle for the compilation to happen.
Sure, but couldn't you say a message is always just a vector of cells?
Oh,
and like compute about a tree.
But you need sometimes you have some additional message.
Oh, so you want that? Okay.
But
right. Because for those you don't want to send about a tree. For example, if you have the response to the output.
Or what if you specify a PIOP? How do you? Yeah. So that's why you have to just basically don't make any sort of arbitrary restrictions and get things to be as general as possible. So for instance, I have let me say what to do with this. Okay, so this is now the how to encode Oracle access to a message. And
I'm guessing you're using the same definition for the instance Oracle, like the implicit instance?
Yeah, the same definitions. So there is just an abstract type of Oracle computations where you could have access to the set of oracles. So let me scroll all the way to the verifier. I guess Oracle verifier here. Okay, so this is a verifier in an IOR, where I assume that every message sent by the prover is wrapped in an oracle. So what this means here is that the prover still actually sends the message, but there is some wrapper around this verifier that prevents the verifier from seeing the whole message and instead establish some sort of oracle interface where the verifier can query. Okay. And so that's why we have this Oracle computation types, where here you have the set of oracles that are all of this. So this part corresponds to the Y part, the implicit instance. And this part corresponds to all the messages in the protocols. And then this is some potential additional oracles that the V might have access to. So it takes in all the things that it can see in full, and then it can query all the things that it has query access to, and then it returns the output statement. Right. So you have here at the very end, you output some X prime and Y prime.
And this oracle comp is like an arbitrary function of the oracles which exist. Some of the oracles have been sent in the protocol, and then they can do something.
Yeah, they can do something. So yeah, it's a monad where you can always make an oracle and then specify what you would do with the response of the oracle.
I see.
Yeah.
So is this like
this is cursor, I think.
Yeah, cursor, which is a VS Code call.
Like VS Code has built-in support for me.
You had a question for something virtual.
Yeah, is this virtual Oracle? This Oracle conf? Or not exactly?
What do you mean by virtual?
I think that I have Oracle access to F, and I want to compute some function H, which is like F plus right.
Okay, yeah. Then you can define an oracle computations where you say here. So like you can write do let response, which is like you query F at some point, I don't know, Q is the query, and then you return R plus 5.
Yeah, cool.
Okay. And yeah, so that's just the X prime part that the verifier outputs. The more difficult thing is how do you precisely define what this Y prime is? So
this is after several rounds now.
yeah, say after some number of rounds, the verifier needs to implicitly specify this Y prime. What would be the most sort of general way to do it?
For defining Y prime?
Sorry?
For defining Y prime?
Yeah, like in general, how would you define this Y prime? Like in an implicit manner where V like doesn't know Y pool.
I specify like a circuit that taking like the oracle, you give it like an index in each of the oracle that you want to query, and then you like kind of like evaluate the function on the answer of this oracle of this query. Something like that, like my Y prime, I find a domain, this domain, I find a mapping to the oracle that I do, and then I kind of like apply a circuit to it, and then give me a value, right? Something like that.
Yeah. Yeah, that's basically the idea.
Okay.
Yeah. So you have some Y prime with some associated oracle interface, and the verifier will sort of gives an implementation of this oracle interface based on all the oracles that it has seen so far. So sort of maybe it goes the other direction actually. Yeah. So it says that later on, if you want to query this Y prime, here's what you do. You do some queries to all of these oracles, and you do some computations, and then you return the result. Yeah. Okay.
Is there a difference in type between this Y prime output and the oracles during the message? During the execution of work.
So it can be arbitrary. Like as the people doing the specifications, we can define what the oracle interface looks like, and so it doesn't have to be the same.
Okay.
Yeah.
Question: do you need to split the explicit and implicit instance? Because you could also think of like the explicit instance as being, things of type that I can read directly, and then I can have things which are oracle compositions, and then I can like simplify it to a single one.
Right. So like it returns a tuple of X prime and
or return an X prime. An X prime may contain many many things. Some of them which are implicitly defined, some of them are explicitly defined. And then, I don't do this explicit split between the two things. Like,
it still exists, right? You're still going to have a tuple of things.
No, sure, but it's simplified. Like instead of like outputting three things, like explicit, implicit, and witness, I just output two things, and then I,
Correct. Of your two things.
Yeah, one of them will contain it, but I'm saying like, but they like.
You're still outputting the same stuff.
Sure, but
putting it in different boxes.
But I think one macro.
Yeah, sure.
Yeah, so that just means that instead of here you have like another product, and then you specify ways to implement the output oracle.
Yeah, I'm just asking because one of the new things I've been writing, I found that if you like just forgo this distinction between explicit and explicit instance, so you just have like one instance which might contain something which depending on the transcript, that turns out to kind of like simplify a lot of the definition that you have to do.
Okay.
So I just, I'm not sure if this is the same case here, but I wanted to mention it.
Yeah. Yeah, I think eventually we're just gonna either split it. Yeah. It's possible either way.
Yeah. Just something to keep on your mind.
Yeah.
I'm sure you have a lot of things on your mind already, but I'm
this is
enough just in case.
Yeah. Thanks. Okay. So that's just defining the structure of the protocol. Next, we can define just what it means to run the protocol. So let's say you give this protocol some initial input, X, Y, and W. Then you can just run it in the intuitive sense. Like you keep going step by step. And in each step, you can record the messages that were exchanged. And then at the end, you output the transcript and everything, and the outputs of both parties. So this is something that you can just define sort of in an inductive manner. So let me go to, say, running. Is there? Yeah. So for instance, this is for just a reduction with like no oracles whatsoever. The oracle, the IOR version is also similar. So you first just run the prover, assuming this is in a public coin setting. So assuming the verifier just returns random or its challenges, and then you run the final thing here, sort of do the reduction at the end. And then you return both of these things. You return both the prover result and the output statement. And that's,
yeah. So you have a notion of what messages are. Is there a notion of ordering of messages?
Yes.
Where does that live?
So it lives in this protocol specification where it is indexed by n. So the spin n is the type of 0 to n-1. And so if you have a function like fin n to type, then it gives you an indexing over the types. Yeah, thanks.
Very good. So the messages themselves don't contain information about where they appear in the protocol, and it's the protocol that knows where the messages are going.
Yeah. Yes, and then once you define how to run the protocol, you can define sort of security definition. So currently I define completeness and then a bunch of soundness notions. I have not defined zero knowledge yet. Yeah. So in terms of the definitions, it is written in terms of this game-based notion, where you can see on a paper, you see something like probability of here's some condition, right? Some condition, and then here is the setup. This is the game. And then you have like, say, at most some error.
But can't you, like just in the world of without cryptography, inductive oracle world, can't you just do it dry without games? I recall you can do this at least for soundness, round by round soundness, because it's just about the fraction of challenges and so on, and doesn't just the existence of a positive answer in the next round as an oracle already guarantees you it holds for any strategy of the attacker and so on.
Yeah, it's in that form. It's still, whenever you write down a probability, please first define what your probabilistic experiment is, right? And then the events that you want to count. So you always have to.
Yeah, but it doesn't. What I mean is, it just doesn't need to refer to external algorithms that choose or whatever,
Sure. Because in the information theoretics, we don't need to talk about efficient algorithms and stuff. So, unbounded algorithms.
Yeah. So that's basically the format that we decided to go with. And so if you look at, say, the definition here for knowledge soundness, it says that there exists an extractor, a straight line extractor for now, such that for all statement and witness and any prover, potentially malicious, if we run this reduction that is composed of the prover and the corresponding verifier, then so here's the condition. The conditions are that you run it with some input, statement and witness, and you return some output stuff. And so this is just like x1, say w1, is not in this first relation, but x2, w2 is in the second relation. Right? This is the bad condition. Will be small, given that you have the setup of the game here. So the main setup is just you run the reduction with, say, logging all the Oracle queries. So this is helpful in a random Oracle world. And you also run the extractor to get the input witness.
So what does the extractor get?
The extractor here gets the input statement, the input statement, the output witness, the transcripts, and all the all the queries of the prover.
So it gets the transcript.
It gets the transcript.
Do you do as normal soundness as well?
Yeah.
Because so I was talking with there's in the IUR definitions compared to the normal. Did you talk with him already about this?
Maybe not.
So there is, okay, in the IOP setting is very clear what soundness is.
Yep.
Soundness kind of like I say, like I do this game and the thing doesn't go in the new relation. Yeah. With soundness there are like two different definitions you can do. So one of them is the one in which I let the malicious prover output a new witness.
Yes.
Or the other one is the one in which I ask that the thing is not in the output of the malicious prover is not in the language of the relation.
Oh, of the verifier, you mean? Like
the output of the verifier is not in the language of the relation.
Yep.
So, but there is no witness given to by the malicious prover.
Yep.
So turns out
you need the second one because when you compose.
Exactly. You get this kind of problem with the soundness composition. So okay, as soon as you've already done it, it's great.
Well, I have not fully done it. I am aware of the problem.
Okay, good.
But yeah.
Okay, good. Yeah, I just wanted to raise it before it was.
Yes. No, definitely.
Yeah.
So the soundness definition that I currently write here is a little bit too strong. Like it's not exactly what you said. It just says that, well, because we don't care about the input witness and output witness, it can be like any type, but this is a little bit too strong in order for knowledge soundness to imply soundness.
I see.
Yeah.
Yeah, that sounds good. Yeah, it's kind of interesting because when you're like in the IOP setting, a lot of things are like extremely, since you're losing to the empty relation, you're like, everything is very clear, but when you have an IOR and you want to figure out how to complete the end of the protocol, then you start having like details in which the right definition is not immediately clear, which is very funny as a thing.
Yeah.
Like this is the same that happened with zero knowledge. Like zero knowledge, by the fact that you have the implicit instance, the IOP definition you could extend to IOR in many different ways, and each one of them they give you like slightly different composition notions.
Okay.
Yeah, but I'll just
we can talk more.
Yeah.
I want to get the right definition in.
Yeah.
Okay. Cool. And with maybe 30 minutes left, let me go to the Fry spec.
Sounds good.
Just one general thing. At least I'm not sure because when I was writing proofs for Stu white paper or whatever, these are all proofs of proximity in the following sense that even in the main statement you prove or the main trace you have committed, it's like even a bunch of committed functions of oracles. There exists a proximate selection, a correlated proximate selection of polynomials which satisfy sufficiently close collection of polynomials which satisfy this and that, which just enforced by the circuit. So I was completely fading away the logic actually of the circuit and what it's supposed to prove, not fading away, I was pushing that to a different thing because it helped me just easier to argue about, to formulate soundness and to argue soundness. Just keeping it as a black box, whatever the circuit means to express in terms of witness and input and output, that's a different thing that can be fully separated from the logic of the rest. I don't know if this input for me now makes any sense.
We did read your recent papers pretty carefully. So you have for soundness, you have a bunch of these existentials. That is Is that right? Like for Fry or Basel, yeah, one of the protocols, for instance, you have like, there exists some, I don't know, polynomial.
Which is proximate and satisfies this.
Right, and that P, encode P is close to the actual code word, C, something like that. And then blah, blah, blah.
And then the multi-linear representation would be
Yes. So because of this existential, you can just fit into this IOR framework by letting P
that's why I'm asking.
be the witness. Right. So if you set P to be equal to the witness, then you have like this general from a relation into a language, right? And this transformation exactly gives you this existential.
Okay.
Yeah, it's kind of like my relation is kind of like.
So the relation is about the proximate. Yeah. Makes sense.
Yeah. So we're showing.
The witness is the proximate.
Yes. Yeah. Okay. So this is a Fry spec. Thanks to Julian.
Thank you. Do you want me to narrate it a bit?
Yeah, if you want.
Oh yeah,
narrate.
Sure. So essentially we obviously start with the parameters are, we have a field F, we have our two smooth subgroup D, right? We have X, which is used, I believe, in the coset, and when we have a coset sort of context, it's the sort of like the value like from which
that's a shift value.
Yeah, exactly, the shift value for the coset.
For the top domain and then
yeah, and then it's X to the 2n, essentially, right? Is the future. And we can look at the definitions in a second. Then we have K, which is a number of folding rounds, because where K is smaller than K is a number of folding rounds because, of course, we can do both early stopping, but also we can do more than even and odd splits in each folding round. We can do 2 to the S
that's the folding
splits.
degree.
Yeah, so we have the folding degree, so we do 2 to the S split, so S equals 1 is the sort of the normal one, right? S has to be strictly positive, so S equals 0 is not permitted. K is a number of folding rounds, so as I said, we we do these K rounds, and so it's a K times 2 to the S has to be less than N in particular, right? And then D is the degree bound on the final polynomial that is returned in the case where we do early stopping, right? So in the trivial cases,
the S can be different from round to round, or
no, the S is fixed here.
I would choose because I mean, the main reason why we use higher, I call it higher reduction factor.
Okay.
In a round is for group size optimizations.
Yes.
And I recall from the Polygon guys that they were choosing different steps.
At each round.
They had given us, if you look at blocky 2, and probably it's also present in blocky 3.
It's not present in blocky 3. This is one of the attributes we never got around to.
Okay, but there was a script written by William, I think.
Okay.
That tried to find just by brute force optimal configurations, and it was not homogeneous. It was not like always use a reduction factor 4.
No, the reason why is because the first round you have base field element. So my folding factor is S. I read 2 to the S element from the initial Merkle tree. So at the start, if I'm reading 2 to the S field element, base field elements, it's better than reading 2 to the S extension field elements because they are smaller. So usually
I don't think it had to do with it because you just process or
no, these are to the proof side.
You do anyway first the patch.
I think you also can reduce how much you commit to, I think. If you do larger than 2 folding.
Exactly, yeah. So usually at the start you want to use a larger folding factor, and then later on you use a smaller one. So there's a lot of benefits on that.
Yeah, the other big thing is that we definitely don't always go down to constantly. Never. But like, if you want to return a final polynomial that isn't constant, so that's very good.
There we allow, that's what the D is for, right? Which is a restriction on the degree of the final polynomial set.
Yeah.
Right. So that we already have. Okay, yeah. So that's an important generalization which we will have.
That D you could actually derive, right? So it's not really needed for the last. Because if you know what's the degree of the top polynomials, you know.
That's true. Actually,
I have like a list of the parameters that I for the calculator, which I have. I'm just gonna double check with them in a minute. You go ahead.
Okay, yeah, I do want to mention we can just support this variable folding degree because we are defining a single round.
Oh yeah, fair point. Fair point. No, but then the top level construction.
Yes, that will need to change.
So that will need to change. Yes, yeah, fair point. Yeah.
So right now, this file. Yeah, this file, which is like almost 2009. This is devoted to just the breakdown of the single rounds of flight.
And I guess you're also not missing the grinding for the moment.
Yes, we don't have the grinding.
We don't have grinding either.
Yeah. Okay, and the read Solomon code, where is it specified which code you're using?
I mean, it's unique once you specify the domain and the degree.
Okay, good. So they won't give you everything. Okay, good.
But then I would rather choose the D as the input degree. No, just say.
Yeah.
Seems to be more natural, but I don't know.
Mm-hmm. Yeah, we can make the variables more descriptive.
Yeah. And then finally we have this size condition. Maybe you can scroll down a tiny bit, which relates D, S, and K. Right. So we have 2 to the K plus 1 times S. All times D must be smaller than or equal. And then we have an I, which is just the index of the carbon round number. Yeah, cool. So I think that's everything on that. And then we have, there's maybe we can scroll down to the first prover, or maybe you have some more things you want to add.
No, that's it. So
let's do this.
Okay. So in terms of, if you think about what does the ith round do, the verifier is going to send a challenge. Prover is going to send a folded oracle, right? A folded code word as an oracle. And so at this point, you should think what should be in the statement, like the explicit and implicit instance. The explicit one, which is the statement there, which is just like the challenges that we've seen so far. The implicit instance, here we have to sort of append all of the code words so far, so F0, F1, ... all have to be in the oracles. And that is because at the end we have some correlated queries. Although, yeah, I think there might be a way to not have this if we have this very, very general simulation semantics.
Yeah.
But that's another point.
Somehow in the future.
Yeah. Okay. Cool. And so the witness here is not trivial. It is the polynomial itself. So at the ith folding, the polynomial has also been folded. And so it's degree bound. So here it just means a polynomial univariate of this smaller given degree. Right? The degree is almost this much. Just some custom notation.
Is it unique? Do we know that it's unique?
No, it's not, right? No, there might be like list decoding. There might be many.
By the time you get to the final verifier challenge, I think it is unique.
Yeah, potentially, yeah. Cool. And so I believe the relation should state, well, this is the part that we're not clear on. Like, yes. What is the relation?
We probably want to discuss.
The input and output of this, given our setup here, which I think is reasonable.
Yeah. Yeah.
Sorry?
That's quite difficult in projects, because you need to take into account at least the way how the proof is written, and I suppose that's going to be formalized in the same way it is.
Yeah.
It's a relation on, or it's a statement, because I'm quite sloppy with my logic notation. It's a statement on the entire collected, the history of
yes.
Oracle.
Yes, exactly.
And yeah, so it's essentially, if you look, I can send, I don't know, do you have this, a copy of the current Stu white paper?
Please send it.
I don't have a lot of copy of this.
It's not that out publicly, but I shared it already here and there. Because I say for one reason, because up to that writing that white paper, I was even like, always when it came down to these consistency measures, I was like, it's a pain in the neck, I just write this. I'm sick of this proof. And this Stu white paper is the first time I did it more in greater depth. like getting clarity about what does consistency measure mean, not just wrapping it in a single sentence. And what does it mean is like, given, it's actually related, that's also quite advertised in Hada's track of work, that consistency checking, because now it's like typically, because it's faster to implement and think that way, it's like now we have the folded oracles, now we would start query, how do we sample? And typically now it's presented like this, you sample a random X from the top domain and then look at its protection trace on the small domains and use these values and their missing minus values to check collinearity. Whereas the initial Fry paper, as well as other work, they actually go, they argue that the sampling of the query goes bottom up. You sample first on the smallest domain.
Oh. No.
Check.
No, I think.
No, that can't be.
You have to sample.
No, which branch you follow? I'm not finished. Okay. So it's now a stochastic process instead of just a single sampling. You do the several samples as follows. You start with the most recent oracle. You sample a random point over the current smallest domain. You check collinearity. That means you require 2 openings along the fiber of the previous oracle, right? And then you decide now, and this is a stochastic game process, which of the 2 I want to have proven that they're consistent either. And so one half is to choose one point along the fiber of the projection. And then you do it the same again. You know, they choose then again the correlate. And the thing is, this thinking in that way, it gives the same distribution as sampling on top domain uniformly and then doing the thing as often nowadays described. But it helps a lot in understanding this consistency measure. But this tells you precisely, if you sample, and this is like, it's a probabilistic process, what is the success probability to succeed? Everything succeeds. So that's the average success, the average consistency, the average success probability of all collinearity checks when you sample fiber-wise from the bottom up, that you succeed in all the checks.
Right.
And these are the measures which are crucial for the whole Fry proof to keep track of the consistency. So everything looking from the smallest current domain from this lens instead from the top domain.
I agree with you with that. The proof, to prove that it works, the verifier makes an observation at the bottom layer and it works its way up. But the sampling happens at the top layer.
That's what's currently practically done, but it's equivalent.
The distribution is equivalent.
But it helps in the proof to understand the notion, and that's how also the next reduction step is actually uses the weighted correlated agreement theorem. So with these consistency weights, it's that keep record of the previous quality of consistency in some sense.
So if you do mutual correlation, it means you can avoid all this weighted stuff, and the tree traversal is a lot easier, like a lot more.
Okay.
So if you had already mutual correlation.
Yeah, correct.
I'm not surprised to hear that, because at some point,
hopefully we can put this out in like a week or 2.
Yeah, that's interesting either. So that it has so much that you hugely.
Yeah, so I guess maybe that, like as Nico said, maybe we post that in 1 week or 2, and then it could be helpful for the.
Yeah. And it's also
because I mean,
the statement of the MCA for the conjecture.
Right. It would show that.
We would need the mutual
correlated.
But given the possibility, let's say, even though I don't believe, say somebody proves up to capacity, but proves on not mutual correlated on, wouldn't be wiser currently, at least to have 2 versions, the one that keeps with the more technical consistency measures, and then the one that is greatly simplified thanks to if correlated mutual MCA would have.
The point is that this analysis is much simpler and therefore probably easier to formalize.
We probably don't have time to formalize 2 proofs. So we would like to stick with the one that's simpler.
Okay. Fair point.
Question, can you like in this case, like if I instead of working through the fold, I work with interleaving of code. So like I start with Solomon code, I do the interleaving now, but I don't change codes, like, because it's kind of like, there is some weird code switching going on, right? But,
like RS codes allow you to code switch.
Without, exactly, but.
Because of how they're built, right?
Yeah, but I'm saying like if I do your analysis and I start using always the same code, but I guess it doesn't really work. You have to use with Solomon really for a fry version. You cannot really, do that.
But how does it simplify? How does it simplify?
It simplifies that. So,
maybe guys, we should focus on this thing. Yeah, like that.
No, I think that's the last thing. We can
We can send it to you.
Yeah, I think I have a question as well, but we can.
Let me just go to the general protocol. So this is, we specify a single round, including the last round, which is different because the prover would just send the final polynomial, so like the folded polynomial, and then verifier.
Non-encoded.
I think.
Oh no, it actually just sends the raw polynomial.
Okay,
It's just a code.
Yeah.
That's what happens.
And you include this as part of like the fry step, but you don't think of it as the trivial IOR. No, I'm just asking, like, are you like sending it at the end as part of fry, or are you thinking of the trivial IOR of proximity where I just send the witness?
No, it does the folding step and then it returns the polynomial.
Right.
So you don't just do the folding and then you like stop compose with the.
Can we show the implementation very quickly?
We can further modularize to make it the trivial ones. Probably makes proving simpler.
It might be easier because then you have single round that's always the same. And final round. Oh, actually, that's sorry.
So. Cool. So it sends the witness at this point. Right. And the verifier is going to send back, it's going to sample, but it also sends back the prover all the challenges that it's going to query. And that's that. And then you just slap all these together to form the whole fry protocol. Which, we just have a function that does the composition.
And you can run this thing.
Not right now.
So we need to plug in, the one thing that's not computable here is the polynomials, because the polynomials in master are non-computable, but we have computable polynomials which we can show an isomorphism with the non-computable ones up to evaluation. Once we plug them in, everything runs.
Good. So, so for instance, this is for all the folding round. Right. And then later on, you have this overall reduction. That is, you append the folding reduction with the query round reductions, and that's the whole protocol.
Very nice.
There we go. Easy peasy. Only took me like 2 months.
Yeah, this like feels like magic.
Yeah. So we've got where is coming next, and then you have a sum check as well.
Do you consider first doing baseball and then bar?
No, we're just doing one.
Well, no, I do have someone doing binary baseball.
Yes, that's true. Yeah.
Is Chungwa even on baseball?
Binary baseball.
Question: with the where are you doing the Reed Solomon version or the interleave code version?
Right now it's Reed Solomon, but we could change it. Where at the America, the state of where is we had some preliminary work done on formalizing a lot of the lemmas and theorem statements. We haven't started on the construction. There are probably a few more minor changes needed on the theorem statements as well. I think in particular folding we need to change.
Because the nice thing about working with interleave code is that then you don't need a different setting for the binary case. Because you can just think of like interleaving of binary thing, the folding does not need to divide, and so this kind of simplified a lot of the analysis at no real at no real cost. So and it's quite nice because you can do it, you can do it for any linear code with no problem, and nice. The only, for any linear code, the verifier will not be efficient, but the rest of the things will work out.
So actually, I mean, we did discuss this a while back in terms of did we want to formulate it in a kind of code agnostic way, and then I think we ended up settling on doing it with Reed Solomon, but I'd be quite open to revisiting that.
Yeah, I think we just need we were
like I don't think it would be a huge
good
change.
abstraction
Yeah.
when we were discussing this.
Yeah.
So if you
I have a very good one. I can give you word in 3 lines.
Yeah,
let's do it.
It sounds good.
If you want.
So actually, the other question is obviously because we've also been following the white paper, but also since then there have been a lot of changes, and so it'd be good to get an update.
You like a very simple, a linear IOR for work, or for any code with very simple everything. Okay. What's my relation? My relation is something. I like this thing more. I don't like writing on paper. I'm gonna. So suppose that I give you like a simple relation. I'm gonna call it RC, which is like my instance is gonna be a vector and a value. S, and it will be like some f-at, and my condition will be that f-at.
By the way, if you want anyone else in the room to be able to read this writing in Greek, it's probably not optimal.
I don't know. Do you like?
Like just as a thought.
We can boost the PowerPoint more.
Yeah, maybe we should.
Because I'm done with the presentation.
Okay.
Is this yours? Anyone?
I think this.
I think Cambridge was in the room.
Yeah.
Okay. So I'm gonna giving you 2 constructions. They're both really simple, and together they give Word with actually better parameters than in the Word paper.
Okay. That sounds pretty good.
Okay.
And if you give us that, add us the proximity generator paper, then we're very happy.
So we have this. Okay.
I actually were allowed to use them.
People have been needing them throughout. I have no idea.
Okay. I hope we haven't stolen someone's food.
No, I mean they've been here all day, right?
Okay. So this is what I am gonna the relation which I'm gonna decide. What is this? This is like linearly constrained codes.
Yeah.
Okay. And you can do for other things. You can do for more complex constraint, but linear constraint is good enough for what I want.
Yeah.
So I'm gonna need 2 building blocks. So the first one is gonna be a very simple linear IOR. So I have a prover, and I'm gonna apply it on RC to the K. Right, this is fine. So prover, verifier, maybe with the 3 lines I was overselling myself. This is already 3 lines.
Well, you had 2 already. So 3 because actually that one is a bit low.
Okay, so what they input on the prover gets the input all the things over here, so X, Y, and W. The verifier gets X and Oracle access to Y. Good enough. Okay, so I'm gonna first. So there is an IOR you can describe, which is just the Samcheck IOR, and this is an IOR from RC to the K to RC, and this is just Samcheck. And this is I'm thinking of exactly Samcheck with folding. This is basically the first step of work. I can also write you basically you think of like a Samcheck of the form weight.
Is this part of the zigzag thing?
Yes.
Okay.
Yes. So I'm thinking of something like a Samcheck of this form, and whenever like I kind of like fold, I also induce a fold on the things, and then you use MCA to prove this. So this is like general Samcheck for code, I call it, because it's a Samcheck for anything which I have of this form. Okay. So you have this. This is a Samcheck you're gonna have to formalize it anyway. So this you already have. So I'm gonna just send you. So this is an IOR, so then this outputs an X star, a Y star, and a W star. For context, this Y star is the folding of this, the the W star is the folding of F, and that star is like the folding of this thing, it's like some new value. But that is kind of what you're for. I'm just gonna send you as a linear oracle. I send you V star. Then as a linear oracle, so I have not to think about auto domain sample at all because it's a real oracle.
Yep.
It's uniquely defined. So I'm just verifying the sample Z1 up to ZP in the domain. And then I'm gonna just simply like so it's incredible how many actions.
What about this one at the start? That's good.
Yeah.
It's purple.
Well,
The purple one is
Oh, okay. It's
oh,
red.
that's very
You
good.
came ready.
But that one works.
It is fine. I got my own thing confident with this one for now. I sold them at DPSL 2 years ago.
Very good.
Oh
yeah, that's
exactly. Magic.
Yeah.
We do this, okay. And now what I'm basically doing is that like this is my interleave code word. I folded it by this, so this will give me some values. So this I get like a bunch of claims. So the claim, what claim do I have? Well, I have the claim of this relation. So this is a claim that I'll just write them here. Claim that sum of S star, this is the witness, so actually the W star with I'm going to just write them out. This is F star and this is F at star. So this is just that F at star, then V star is equal to sigma star star. This is the first claim. And now this claim, what do they tell me? Well, they tell me that when I have F at star and I encode them with the code C, he agrees with Y star at the position Y. So rewriting this means that for all I in T, I get that code of F star at position at psi is equal to F star at F psi. Right? This is just saying that when I encode and I check, I get the same value as the code for it. This is the spot checksum or the in-domain samples. And this is if and only if. This is the same as like saying like, look, DG is generated coding of the matrix time F star at Xi is equal to this F Xi star. These are linear constraints as well. These are exactly linear constraints. So I'm going to just sample some randomness, epsilon, and I'm going to check this the claim that sum of epsilon I times this constraint. So this is going to be. I write a sum check just because it's prettier, but this is like G C of the Xi B times. Okay, I'm gonna go then F at B is equal to the sum of the other things. You also want this claim inside there. You're just batching all the claims together with the same randomness.
Or it can be some other.
You can use any zero evader here. Is fine. So this is a reduction. What's the soundness? Well, the soundness of this is kind of like the soundness of sum check. So this is like the soundness of sum check. So this is where MCA comes in, plus 1 minus delta to the t, or for the delta that spits out by the sum check, plus in this case it's like t plus 1 over f. Because this is kind of like the error of this batching step.
Should we think of this as round instead?
Yes, yeah. This is all round around. I'm just doing soundness for simplicity, but this is round around. Yeah. Okay. This is a linear IOR. Of course, now I want to compile it to. We have another one. So this is nice. So now what I'm gonna do? There's this very simple code. Look at this signature people.
Yeah.
They didn't know what's going on.
Okay, fine. I just found a random tissue in my pocket. Okay, it's fine. It's done now.
It's fine. We have to work with action. So suppose that I give you like a one round linear IOR with a single query. So what you think? Okay, I send you like an oracle. Maybe I have other messages, but I'm going to send you one linear oracle. The verifier sends some randomness, and then he makes one query P. I can very easily translate this into an IOR. So this is like a linear IOR. I'm gonna say this is from like R to R prime. I can turn this into a point query IOR from R to R prime times RC for any code that I want. So for any code that I want, it doesn't even need to be that code. For any code, I can do this. What's the transformation? Well, say that this value was called F, coincidentally, weird it's called F. So the transformation is that I just send you as an oracle the encoding of F. The verifier does an out-of-domain sample. So I'm going to call this, say this is the X out-of-domain sample, and then I give you the answer.
Several.
Oh yeah, you can also do more than one. You can do more than one, but think of like a single one for simplicity. And then, you know, what are my constraints? Well, the out-of-domain sample will kind of like tell me that sum of a path times, say that this was a multilinear out-of-domain sample, you can do different one. You have x that is equal to y, and then you have the constraint from this query. So it's like sum of like yeah, b is equal to some answer. If you want, you also batch them. Like you can also do like a single round of batching over here. And yeah, this is just, you know, you have whatever the verifier would output for the first thing plus this. And now what do you do? Okay, so I have like a linear IOP for our p to the k. Then I compile it by this transformation to a point query IOR from RC to the k to RC prime for any code prime that I like. And then I just curve. I can just take any other one and I just apply this to, I compose it with this IOR, right? This is the inductive step. And until I go to the trivial IOP, which is the one where I just send the witness. So with these two things, basically you can do war with every code by just this. So, and I think it's relatively simple because this compiler does very little amount of batching. You don't have to do much. You just kind of like, you just do out-of-domain sample. You can use also the, you know, in warp.
What if we don't have this out-of-domain sample?
So you can do it also when you don't have the out-of-domain sample. The kind of issue is that basically, okay, so what's the error, the round-around errors of this thing? Well, so here you have like kind of like the error of out-of-domain. Is the first term. Then okay, here is where I would get like the randomness of the linear IOP. So this round here will have some error, which is kind of like the mass of the error of the linear IOP, and the batching error, which I haven't bounded too well, but I think it's either like it's probably like list size over f, depending on what derivator you use. And you see that this part here does not depend on the list size. This I get exactly the error of the linear IOP. So in particular, this part here, which was my error of the linear IOP, will not depend on the list size. If I don't do the auto-domain sample and I'm working in list decoding, then this error will become multiplied by list size, which means that my number of queries becomes a shit ton. So that's why I need to do this auto-domain sample here.
The other thing is, this is called like a completeness relation, like if things are good, right?
Yeah.
What about the soundness?
Yeah, so sound.
You need to add the proximity.
Yeah, so yeah, absolutely. Like soundness, you get like these are the proximity relations. So like the delta of like f from this relation would be kind of large. The soundness of this sum check, I can give you the proof, is not. Is basically, if you look at the state restore, yeah, then round soundness proof of work, the initial step is exactly this thing. And you'll see that it doesn't really use the fact that we're using with Solomon codes. It just uses the, so for soundness of this, I just literally need a bound on the list size of the code for this error, and a bound of the mutual created agreement for the sum check part.
Yeah.
And
concretely, how we can change this relation to make sense of soundness.
I think that what I did was just like,
sure, you add like some distance between the f and the c of that hat.
Yeah.
Right? Do you still have the second position like exactly?
Yes, because this is about the witness.
Okay.
Yeah. So you want the condition exactly. You want some kind of proximity. But
yeah.
in general, like what you want to say is kind of like, this is like your implicit instance.
Yeah.
That there, like you want to say like for anything it evolves, it will not satisfy this constraint.
It will not
satisfy this constraint in the soundness case.
Sure.
Exactly. So this is kind of like.
So yeah, for knowledge soundness, let's say. So then you also have this f hat.
Exactly. Yeah.
Debrief in 5 minutes.
Okay, perfect. In the other room?
Yeah, in the base.
Perfect. So yeah, so I'm saying like for all u in the list of f at distance delta, UV is different than U. It's kind of like the soundness that I get. This is what I want to model in the soundness case. Yeah, and it is relatively clean. It works for any code. If you want to do zero knowledge, I just put here a zero knowledge subject, so it just works.
But what about the code work?
It doesn't really matter because, like, I'm in a proximity thing. I'm in a proximity thing, so I can query the input, and querying the input is for free. Like, it doesn't really, if I even for IOPs, if I have like the definition of zero knowledge is kind of like the view of prover, verifier on X, Y, and W. This is the honest thing. It is distinguishable from the simulator, which also get access to Y.
Sure.
So, like for in this particular reduction, like the subject will query, this f prime is the fold of the original f, so I can query it for free. So.
Yeah.
And these values here to get like once I query, I know them, so it's fine.
So the view consists of the transfer and also the output.
Yeah, if you want, I can show you like let me get my laptop. I'll show you the definition of zero knowledge for IORs because it might be useful.
So maybe before that, so let's say we have this RC that also acts in the proximity parameter.
Yeah.
Right. Then knowledge soundness. It's like
yes,
you have this IOR.
Yeah.
You have the input. You have the output relations. And so they have some different proximity parameters.
Yes.
Right. And the error, this delta here, will be dependent on those two parameters according to these proximity guidelines.
Exactly. Yeah, like basically this subject this error here will depend on which proximity parameter you give, and there will be an input and you can model it as an input and output opportunity parameter. So this also models like